Far from Earth, Jupiter's moon, Europa hides a secret beneath its frozen shell, a vast ocean that could cradle life. But what truly lies in that dark hidden sea? In this video, we'll journey into one of the greatest mysteries of the solar system. If you enjoy it, please like, subscribe and share, and tell us in the comments what you think might be waiting under Europa's ice. Thank you for watching. Now, let's begin. The shell is bright against space and shows water ice across almost every reach of the ground. The brightness is not even. It is written with ridges, bands, blocks, pits, domes, and wide fields of jumbled pieces. Long lines cross the plains for great distances and keep a steady course until they bend in gentle arcs. Many of these lines appear in pairs. Each pair forms two raised walls with a narrow trough between them. The two walls run side by side for tens or hundreds of kilometers and keep their spacing with quiet persistence. In low sun, the walls cast fine shadows that sharpen their form and show that they stand above the plains. Where pairs meet, one often crosses over the other with only slight disturbance, so the order of events remains clear on the surface. The troughs can hold bright frost as if the topmost layer there is fresh or finely grained. The paired form repeats often enough to give large regions a rhythm of evenly spaced lines. Between the pairs, the plains are offset by small amounts, as if the ground had opened, slid a little, and then settled again. Bands add a second, broader pattern to the shell. A band is a stripe of terrain that is darker and more finely textured than its neighbours. Inside a band, rotated blocks lie like shuffled tiles. Each block keeps the look of the plains from which it came but sits at a new angle. Along the margins, sharp lineations mark the edges with clarity. Inside, faint grooves run along the length, suggesting a steady direction, stamped into the new material as it cooled and became part of the crust. Some bands are narrow ribbons. Others widen into corridors that can be traced for great distances. Bands commonly align into belts that wrap partway around the globe, then fade as other features take over. Chaos terrain interrupts both plains and bands. In these areas, rafts of older crust float within a smoother matrix that later froze hard. The rafts are blocks that have been lifted, tilted, and rotated. They carry on their surfaces the ridges and lines they held before the disturbance, so each raft preserves a small map of the ground's earlier state. The surrounding matrix fills gaps with gentle curves and soft edges. Some chaos fields form nearly circular patches, others stretch along a trend as if guided by a deeper structure within the shell. The contrast between angular rafts and smooth matrix gives these fields a distinctive look that is easy to pick out from far away. The plains between the large features are not blank. They hold subtle undulations that become clear when the sun sits low. Low domes rise gently above the average level, and shallow pits sink below it. The domes are soft in outline and lack central peaks. The pits are broad and shallow, with rims only slightly higher than their floors. Together, these forms occur in swarms that give parts of the plains a knotted texture at small scale. Elsewhere, sets of tiny ridges create faint corrugations that run for tens of kilometers and then fade. In places, small dark spots and small bright spots appear together like freckles, each only a little different from the surrounding plain, yet persistent over wide areas. Colour marks the ground along with shape. Most of the shell shows blue-white tones typical of water ice, but thin stains of brown and rust gather along fractures at the flanks of ridges and in low places within chaos. The stains are subtle yet persistent and are strongest where the surface has opened many times. Their distribution suggests that impurities travel with briny material that visits the surface and then freezes, or that charged particles have altered the uppermost ice where it is most exposed. Freshly opened cracks often look brighter than their surroundings, as if fine frost coats them. Older lines and older patches grow dull and slightly darker, as countless tiny grains roughen the skin and hold shadow. Craters are present but uncommon for a world that lives within a busy system. Many are shallow and softened at the rim, as if made in a surface that yields and later relaxes. Some are sliced by fractures that pass through without care for the circular outline. Others are partly buried by bands that continue on as if the craters were not obstacles. The scarcity of deep, sharply preserved craters allows the ground to read as young in many places on geological scales. The crust renews itself in pieces over spans of time that are long to humans yet short to the shell. The renewal is not a single event but a slow pattern of addition, motion and refreezing that edits the record without fully erasing it. Light and cold guide what can be seen. The sun is distant, so sunlight warms little and mainly illuminates. Daytime brings a small rise in temperature at the uppermost skin of the ice. Thin coatings of frost can sublimate and settle again nearby, changing texture in ways that shift brightness by a small amount. Night returns the skin to deep cold. There is almost no air to hold heat, so the ground radiates its warmth to space and grows crisp. This gentle daily rhythm freshens outlines when shadows lengthen and softens them again under higher sun. The result is a surface that changes its look with the angle of light, while keeping the same forms beneath. Stress fields leave signatures in the way lines intersect and overprint. In one tract, a family of fractures runs roughly parallel for great distances. In a later episode, another family crosses the first at a new angle. The second family looks crisp, while the first looks softened, so the order of events is plain to read. Near the equator, long, nearly straight lineations are more common. At higher latitudes, repeating arc shapes appear more often and string together into cycloidal chains. Around some older chaos patches, newer lines bend or terminate as if the structure there resists further motion. The pattern is global, but not uniform, with belts of one style giving way to belts of another style across the surface. Scale matters when this ground is read. From a distant view, the shell looks simple with bright planes cut by dark lines. From a closer view, every plane holds swarms of small domes and pits. Every ridge shows a crest and flanks with fine gullies. Every band contains its own internal slices and grooves. Even the darkest stains break into many tiny patches that gather in low spots and at shadowed edges. The complexity is cumulative rather than chaotic. Larger features are built from smaller ones, and the same basic shapes recur at many sizes. Despite the deep cold, the impression is not of a motionless crust. The ground looks as if it has been taken up many times and reset with care. Blocks have shifted a little and then stopped. New material has arrived in narrow strips. Older surfaces have rafted, tilted and settled into place within younger fill. The record is careful and ordered, showing orientations, offsets and cross-cutting relations that allow a clear reading of which event came first and which came later. The shell acts as a firm lid near the top and a responsive body below, able to accept strain and distribute it into forms that keep their shape. Taken together, these traits reveal the present face of the shell. It is bright and faintly stained, carved by persistent pairs of ridges. It carries broad bands built of rotated blocks and smoother fill. It holds fields of chaos where rafts of older crust are locked within a younger matrix. It shows few deep craters and many overprinted lines that point to repeated events. It shows domes and pits that rise and sink only a little, but do so over wide areas. It shows belts where one kind of feature dominates for a while, and then yields to another kind with distance. This is a quiet, legible scene. Nothing rushes. Lines extend to the horizon and beyond, and the slight relief casts thin shadows that drift with the sun. Each feature remains in place and keeps its clue. Together they present a shell that accepts stress, opens and seals, shifts and settles, and records its motion as a calm, repeating pattern on a bright, icy skin. The thickness of the shell is not measured directly, so it is inferred by several lines of evidence that point to ranges rather than a single number. The first line is how the shell bends under loads. When a ridge or a band forms, it adds weight along a narrow line or strip. A stiff, thick shell bends only a little and spreads the bend over a wide distance. A softer, thinner shell bends more steeply and keeps the bend close to the load. Around many ridges, low troughs and gentle bulges can be traced for some distance, which means the shell carries stress over many kilometers. This supports a shell that is not paper thin, yet the relief is modest, which means the shell cannot be extremely thick either. Matching the shape and wavelength of these bends to models of ice under gravity gives estimates that favour a shell of several to many tens of kilometres in thickness. The second line of evidence comes from tides. Jupiter pulls strongly on the Moon, and neighbours tug as well, so the body flexes on every orbit. How much the surface rises and falls depends on how easily the interior yields. If the shell sits on liquid water, the ice is partly decoupled from the rocky interior and can move more freely. Spacecraft measurements of gravity and shape show that the body responds in a way that fits an outer shell riding on a global ocean. The exact thickness of the shell affects the amplitude of this response. Models that match both the overall size of the tide and the pattern of gravity change again place the shell within the same broad range of several to many tens of kilometers, with thinner values allowed where heat is greater and thicker values allowed where heat is lower. The third line of evidence is found in the form of impact craters. On a very rigid cold crust, crater walls stay steep and deep for long spans of time. On a crust that is underlain by warm, slowly flowing ice, crater rims relax, and floors rise as the material creeps. On this surface, many craters are shallow and smoothed, and some appear cut by later fractures or partly filled by bands. The scarcity of large, sharp craters and the relaxed shapes of many small ones indicate that the shell can flow at depth on timescales that matter for landscape change. The depth at which flow becomes easy places an internal boundary between brittle ice above and warmer, softer ice below. That boundary depth linked to temperature and stress is consistent with a total shell thickness that leaves room for a deep ocean beneath. A fourth constraint comes from simple heat balance. Inside the Moon, heat comes from two main sources. Rocks release heat slowly through the decay of natural radioactive elements. Tidal flexing adds heat by turning orbital energy into internal friction. That heat must move upward and escape to space through the shell. The surface is very cold because sunlight is weak at this distance, and because there is almost no air to hold warmth. The top of the shell tends toward the surface temperature, while the base of the shell near the ocean tends toward the melting point set by pressure and salinity. If heat moved only by conduction, which is the direct passage of warmth through a solid, then a thicker shell would carry less heat for the same temperature difference. To carry the observed or expected heat, the shell could not be too thick, or the gradient would become too steep. However, ice that is warm at depth can begin to overturn slowly in broad cells, a process called convection. Convection allows heat to move upward more efficiently without requiring a very steep temperature gradient. If convection is active, the shell can be thicker while still delivering the same heat to the surface. The pattern of surface features hints that both modes may act at different depths or in different places. Smooth plains with small domes and pits suggest slow overturn at depth. Stiff behaviour along ridges suggests a strong colder lid at the top. A fifth clue is seen in chaos fields and wide bands of new terrain. These features imply that liquid or slushy material can come near the surface, and that the shell can open locally and then heal. For liquid or slush to intrude without breaking through everywhere, the shell above must have some thickness and strength. At the same time, the ability to lift and rotate large rafts or to spread new band material over long distances suggests that warm, weak zones exist within the shell and that the shell is not uniformly thick. Taken together, these signs favour a shell that varies in thickness across the globe. Warmer belts, perhaps linked to tidal heating patterns, may host thinner shell with more active bands and chaos. Colder belts may host thicker shell with fewer signs of recent opening. Spectral stains along fractures add one more thread. Hydrated salts and radiation products gather where the surface has opened many times. This points to repeated exchange between the shell and the briny water beneath. Efficient exchange over long distances is easier if parts of the shell are not extremely thick. Yet the absence of wide, deep collapse pits and the persistence of large coherent blocks indicate that other parts retain great strength and thickness. A cautious synthesis uses all lines of evidence at once, bending under loads, tidal response, crater, relaxation and heat flow each admit a range. Where the ranges overlap, they support a shell that is on average many kilometers thick, with a fair chance that it reaches many tens of kilometers in colder regions. In warmer or more stressed corridors, the shell may thin to only several kilometers, especially if convection carries heat upward and if brines rise to shallow depths. The ocean beneath remains global in these models and has enough depth to decouple the shell from the rocky interior so that tides remain strong. Uncertainties remain, and they matter. Ice strength depends on grain size, on the amount of salt within the ice, and on how quickly stress is applied. Heat production depends on the rock content, its mineral makeup, and the exact pattern of tidal flexing. Surface temperatures vary with latitude and with the efficiency of the uppermost frost in reflecting sunlight. Each of these factors shifts the preferred thickness by several kilometers. The most careful view treats thickness as a field that changes smoothly with position and with depth, rather than a single uniform number. In that field, a cold, brittle lid a few kilometers thick rides on a deeper zone where ice is warm enough to creep, and that deeper zone sits above liquid water. Features at the surface then reflect how stress and heat move through this layered shell. Where the lid fractures in a consistent direction, double ridges appear. Where warm ice rises in gentle cells, small domes and pits appear. Where warm brine reaches higher levels, chaos disrupts and then refreezes. All of these require a shell thick enough to support long lineations and large blocks, yet thin or soft enough in places to permit slow circulation and local intrusion. The result is a constrained but flexible picture. The shell is not razor thin. It is not a stone wall. It is a layered living thickness set by the steady exchange between deep heat and surface cold, with values that lie in the broad but informative span of several to many tens of kilometers, and with local departures where tide's composition and grain structure conspire to thin or thicken the ice in measured, patient ways. Evidence for a hidden ocean arrives through the way the moon responds to a changing magnetic field. Jupiter carries a strong magnetic field that turns with the planet and sweeps past the moon like a moving pattern of invisible lines. As this primary field grows and fades and shifts direction, any electrically conductive layer within the moon feels that change and responds by driving small currents. Those currents create a secondary magnetic field that tries to oppose the change in the primary field. The result is an induced field whose strength and timing depend on the depth, thickness, and conductivity of the layer that hosts the currents. Rock that is cold and dry carries almost no current. Solid water ice that is pure also carries almost no current. Liquid water that contains dissolved salts carries current well. A global ocean of salty water beneath the shell therefore provides a natural way to make an induced field that can be measured by a passing spacecraft. The logic is simple but strong. If the moon contains a global briny ocean, then a time-varying primary field should produce a measurable induced field whose direction is set by the way the primary field changes. If the interior were all rock and ice with no layer of high conductivity, the induced field would be weak or absent. The way to test this is to fly by many times sample the magnetic field at different positions along the path and look for a signal that is the right size and points in the right direction to be an induced response. When those measurements are taken and compared to models, the pattern that best matches the data is a conductor that wraps almost the entire globe at shallow depth beneath the shell. The explanation requires only natural ingredients. Jupiter provides the changing field. The Moon provides a thin skin of cold ice, a deeper shell of warmer ice, and below that a layer of salty water that can carry current around the world. The induced field lines curl in a way that opposes the change of the primary field, and the timing of the response lags slightly, as a physical conductor cannot react instantaneously. The amount of lag and the amount of opposition together set limits on the conductivity and thickness of the layer. Too thin and the induced field would be small, too resistive and the lag would be wrong, too deep and the amplitude would fail to match. The best fits cluster around a case where a layer only a few tens of kilometers thick is present within the outer, few tens of kilometers of the body, and that layer conducts like salty water. The concept of induction can be explained in simple terms. When a changing magnetic field passes through a conductor, it pushes charges into motion along loops. Those moving charges make their own magnetic field that tries to cancel the change. If the driver speeds up, the response grows. If the driver slows, the response fades. If the driver reverses, the response reverses. The amplitude and the phase of the response carry the signature of the conductor. The spacecraft records the total field, which is the sum of the strong driver from Jupiter and the weaker but telling response from the Moon. By subtracting the known pattern of the primary field and the expected draping of charged particles around the body, investigators isolate the residual that behaves like an ocean ring. That residual is not random. It rises and falls with the geometry of the orbit. It points in the directions expected for a loop within the Moon. It shows the same broad form from pass to pass, even as the trajectory changes, which is hard to explain without a global layer. If the conductor were limited to a local pocket, the signal would fade when the track passed elsewhere. Instead, the response persists around the world. The ocean explanation also fits with other clues. The surface shows signs of salts, which is what a body of water in contact with rock is expected to carry. The shell shows widespread evidence for cracks and bands, which are ways for fluids and brines to communicate across the lid. The warm base of the shell reaches the melting curve for water with dissolved salts, which allows a liquid layer to be stable for long spans of time. All three strands support the idea that the induced field is not a trick of plasma alone, but is rooted in the interior layout. There remain uncertainties, and they are practical. The magnetic environment around the Moon is complex because charged particles stream along Jupiter's field lines, and because the Moon itself blocks and disturbs that flow. Removing those effects cleanly is not simple and requires careful modelling. The primary field also changes with time as Jupiter rotates, so the phase relation between driver and response must be tracked with care. Even with these caveats, the case for a conductive global layer is robust because entirely different passes at different longitudes and latitudes tell the same story. The interior layer need not be pure water. A salty solution of common minerals would be enough. The exact mix, such as whether the salts lean towards sulfate or chloride forms, is not fixed by magnetics alone. The conductivity range is broad enough to allow several brine recipes. What matters for the inference of an ocean is that the carrier is a liquid containing ions in solution. A global briny layer satisfies that requirement, and does so while matching how the shell behaves above it. The magnetic method has an important property that suits this world. It does not require direct contact with the liquid. It only requires that the liquid encircle the body so that currents can flow around. That is why a global ocean reveals itself while a shallow, isolated pocket would not. The method is also most sensitive to layers near the outer part of the body, which aligns with the shell's inferred thickness. The ocean need not be very deep to make a strong signal, but it must be continuous, and it must be salty enough and warm enough to remain liquid. The image that emerges is quiet and clear. Beneath the bright crust lies a shell with a cold lid and warm lower parts. Beneath that shell sits a layer of salty water that wraps the globe. As the giant planet turns, its magnetic field sweeps past and slowly changes. The hidden layer answers with small, steady currents. Those currents draw a ring of magnetism around the moon that can be sensed by careful instruments. The amplitude and the timing of that ring are not a guess. They are measured, and they align with the behavior of saline water more than with any other plausible material in that position. Through this exchange between a turning field and a quiet conductor, the unseen becomes present, and the ocean below the ice is revealed not by a splash or a crack, but by a gentle, repeatable answer to a change that never stops. Tides act on the moon at all times because gravity from the giant planet is strong and the orbit is not a perfect circle. A tide is a slow deformation of a body under uneven pull. The side that faces the planet feels a slightly stronger attraction than the center, and the far side feels a slightly weaker attraction. This difference stretches the body along the line that joins it to the planet and compresses it in directions at right angles. If the orbit were exactly circular and the rotation were locked so that the same face always pointed to the planet, the tide would settle into a steady shape and would produce little heat. The orbit is slightly stretched, and that small stretch causes the distance to change during each path around the planet. The strength of gravity changes with distance, so the tide grows and shrinks and shifts with position along the orbit. The ice in the interior follow that changing pull and lag behind it by a small amount, and that lag is where heat appears. The lag arises because real materials do not respond instantly. Ice has some stiffness, so when it is deformed it stores a little energy like a spring. Ice also has internal friction, so a part of the energy that goes into deformation is lost as heat each cycle. The balance between stored energy and lost energy depends on temperature, grain size, the presence of brine, and how quickly the tide changes. Warmer ice softens and yields more easily, which increases the fraction of energy that is lost as heat. Colder ice resists and returns more of the energy elastically, which reduces heating. In the moon, the uppermost layers are very cold and strong, while the deeper parts of the shell are warmer and weaker. This natural layering concentrates most tidal heat in the lower shell, where creep is possible, and in any liquid layer beneath where moving water and friction at boundaries add dissipation. The tide is renewed each orbit because a resonance of 3 bodies holds the path slightly stretched. For every 4 orbits of the innermost large moon, this moon completes 2, and the next large moon completes 1. This pattern keeps the timing of gravitational tugs consistent, which prevents the orbit from relaxing to a perfect circle. As long as the resonance holds, the orbital stretch persists. The tide keeps changing, and heat continues to be made. If the resonance were absent, the orbit would slowly circularize and heating would weaken. With the resonance present, the moon remains gently flexed at a steady rhythm that repeats over many passages around the planet. The distribution of heating within the shell is not uniform because stress and strain vary with latitude, longitude, and depth. Near the equator, the tide stretches the surface along lines that change orientation during the orbit. This produces zones where stresses open cracks during one part of the cycle and close them later. At higher latitudes, the pattern shifts into repeating arcs that trace the path of the stress field as it turns. Mapping these patterns and their changes through time helps to locate where energy is being spent. Where the shell is thin or warm at depth, strain localizes and more heat is made. Where the shell is thick, strong, or cold, strain spreads out and heating is lower. The result is a patchwork of belts and corridors that over long time scales can align with observed bands, double ridges, and fields of chaos. Heat also appears in the hidden water layer. As the solid shell above and the rocky interior below flex, the ocean is stirred. Currents flow along the base of the ice and along the top of the rock. Where flow meets a boundary, it rubs, and this rubbing converts motion into heat. Narrow gateways within the shell, if present, can focus currents and increase mixing. Salinity gradients and temperature gradients add to the stirring by driving weak circulation even in quiet times. The net effect is to spread tidal energy into the ocean and to deliver part of it to the underside of the ice. This underside can then melt slowly in some regions while freezing in others, depending on whether the local heat supply exceeds or falls short of what is needed to hold the interface at its melting point. The rocky interior is not entirely rigid either. When tides flex, the rocky part, tiny shifts along minerals and microcracks, dissipate energy. The total heat from rock flexing depends on the mineral makeup, the presence of any water within pores, and the size and distribution of cracks. If the rock hosts water at high temperature and pressure, chemical reactions may be promoted by warmth and by flow. The mechanical heating in rock is hard to measure directly, but it acts as a quiet, steady source that adds to the budget set by ice and ocean. In this way, all main parts of the interior contribute to the total tide-driven heat, each according to its ability to lose energy when forced. The rate of heating depends on the frequency of the tide and on how far the material lags the driving force. The frequency is fixed by the orbital period, which is little more than 3½ days. The size of the lag depends on properties that change with temperature and with the presence of impurities. Salt within the lower shell can lower the temperature at which ice begins to creep rapidly. Fine grains of ice can slide past one another more easily than coarse grains. Warmth produced today further softens the material that will be forced on the next cycle, which increases heating until a balance with cooling is reached. Cooling occurs by conduction through the shell by any slow overturn within the warm lower shell, and by radiation to space from the surface. The balance between steady heating and steady cooling sets the long-lived thermal state. Tidal heat chooses paths as it moves upward. In some places, the lower shell becomes warm enough that buoyant lumps of weak ice begin to rise slowly. These lumps carry warmth and any dissolved impurities with them toward the cold lid. As they near the top, they freeze and spread laterally, losing heat to the surroundings. In other places, layers of ice within the shell remain strong but are broken by repeated stress. Briny slush can be squeezed along these fractures and can refreeze to build the double walls of paired ridges. Where the shell receives more heat than average, larger zones can weaken and detach into rafts that drift a little in a softer matrix before freezing in place. Each of these responses translates the invisible act of tidal flexing into visible marks on the surface. The spatial pattern of heating can change over time as the orientation of the orbit and the spin axis shift in small ways. A slight tilt of the spin axis with respect to the orbit plane can introduce a season-like modulation of stress. A small wobble of the rotation can cause tiny changes in the direction and timing of maximum strain. These variations are modest, yet over long spans they can pass belts of higher energy around the globe. A belt that once favoured one longitude can later favour another, producing families of features with different orientations in the same region. The shell then preserves a record of drifting stress fields. that add to the story told by the present geometry. It is useful to think of tidal heating as a budget with entries on both sides. On the input side are orbital energy and gravitational tugs that repeat with clock-like regularity. On the output side are heat within rock heat within the ocean, and heat within the shell, plus the slow mechanical work of moving and breaking ice. The surface radiates the sum of all these inputs as far infrared light to space. Because the sun is weak at this distance, most of the energy that leaves the surface at night and day alike began as tides and a slow decay of natural radioactivity within rock. That steady escape at the top is what fixes the slow ongoing pace of change within the shell. In this picture, tides are not a storm or a sudden event. They are a patient driver that acts with the same rhythm again and again. The moon flexes, the response lags, energy turns to heat in measure with that lag. Warm zones shift, rise and cool. Cold zones strengthen and resist. This cycle renews on the next passage and the next. Over spans of time that are long to humans but normal to the system, this calm repetition shapes the shell from the base upward. The result is a world where the surface looks quiet while the interior keeps time, and the slow work of tides provides the conditions that allow ice to move, water to circulate and heat, to find paths from the deep to the night-side sky. Double ridges are among the most persistent forms on the shell, and they share a simple cross-section. Two narrow walls rise with a shallow trough between them, and the three features run together for long distances with nearly constant spacing. The regular geometry points to a repeatable process that adds material along the edges of a central fracture. The driver is stress that opens and then closes the fracture on a steady cycle. Tidal flexing pulls the shell in directions that change during each orbit. When tension peaks, the crack gapes by a small amount. When tension relaxes or switches to compression, the crack narrows again. The cycle repeats without haste, and each episode leaves a small imprint that accumulates into a ridge pair over time. The material that builds the walls begins as liquid or slush within the lower shell. Warmth at depth and salts mixed into the ice allow small pockets of brine to persist between ice grains. These pockets connect along thin pathways that act as a pump when stress changes. When surroundings are squeezed, pressure in the brine rises. When surroundings relax, pressure falls. The net effect over many cycles is an upward push along any open fracture, because brine is slightly buoyant with respect to the cold ice above. As the slush ascends, it meets lower pressure and lower temperature. Part of the liquid freezes within the crack. Freezing expands the water by a small fraction, which presses outward on the crack walls. That pressure lifts and thickens the edges, and the growth preserves the line of the fracture as paired relief. Other additions help the walls grow. Shear along the crack flanks grind small chips from the edges. The chips fall into the opening and are locked in place when the fracture closes and water freezes around them. Where opening is quick, a small amount of liquid can reach shallow depth and vent as a fine spray. The spray freezes into frost and falls along the walls and into the trough, leaving bright streaks that fade as grains coarsen and as dark dust settles from tiny impacts. Where opening is slower and shallower, the liquid remains below the surface and thickens the hidden core by freezing from the margins inward. In both cases, repeated pulses add thin layers that build the walls by quiet accretion rather than by any single burst. Measurements of slopes and shadows show that double ridges commonly stand a few hundred meters high and span a few kilometers from outer flank to outer flank. The trough is usually narrower than the full width and may hold bright frost or thin stains. Heights and widths drift gradually along a ridge, which implies that the supply of slush and the ease of opening both vary with position. Where the walls diverge and the trough widens, the ridge often looks lower because the available material is spread thin. Where the walls draw together and the trough narrows, the ridge tends to look higher and sharper. Slight changes in depth to warm ice at the base of the shell, slight changes in salt content and slight changes in the local stress field are enough to produce these smooth variations. Orientation follows the stress field that rules at the time of growth. Near the equator, a stable direction of pull during many cycles produces long, straight segments, organized into belts that can be traced for great distances. At higher latitudes, the direction of maximum tension rotates during each orbit, and the active crack advances in short arcs. The arcs join at angles and form chains that step across the surface in a cycloidal path. Double ridges can run along these arcs as well, which gives some ridge fields a beaded look when seen from above. Cross-cutting relations between belts with different azimuths reveal shifts in the dominant stress through time. The younger belt looks sharper, while the older belt appears softened and sometimes offset. Composition matters for how ridges form and endure. Ice that holds salts and fine grains yields more easily than pure coarse ice. Salts lower the temperature at which water stays liquid, and lower the temperature at which ice begins to creep. Fine grains allow sliding along boundaries and speed the ductile response at depth. Both effects help the pump that moves brine and ease the rise of slush. Both also slow the healing of fracture walls by sintering, which is the gradual welding of ice grains into a stronger mass. Ridges within salt-rich corridors therefore maintain crisp crests longer, while ridges within cleaner ice tend to round sooner under the same surface conditions. The central trough records what happens after each pulse of intrusion. During a warm phase, the crack fills with slush that warms the surrounding ice by a small amount. When the phase ends and pressure falls, part of the liquid freezes and part drains downward along the same pathways that brought it up. Loss of support near the center allows the roof to sag slightly, leaving a shallow channel between the walls. If some liquid vents as a spray, the trough receives a line of bright frost that later grows dull as grains coarsen and as dark grains settle from micrometeoroid impacts. If the liquid carries dissolved minerals from contact with the rock at depth, thin films of salt may remain along the groove. These films stain the floor and the lower flanks and add to the color contrast that outlines many pairs. Not every double ridge requires a steady supply from deep sources. Near-surface lenses of brine can collect within porous layers or along gently dipping seams created by earlier events. Repeated strain pumps small volumes of liquid into such a lens. Freezing along the edges of the lens builds pressure because new ice takes more volume than the liquid that it replaces. Pressure lifts the roof by a small amount and pushes ice to both sides. Over many cycles, the action builds a pair of walls above the lens even if the deeper shell remains relatively dry in that location. The near-surface case explains short ridge segments that begin and end within planes, and shows why some pairs can form without clear links to long fractures. Fault motion can assist ridge growth in corridors where the shell experiences shear as well as opening and closing. If the two sides of a fracture slide past each other by a small amount during each cycle, small steps form along the walls. Loose blocks fall into the space and are trapped when the crack closes. Refreezing welds the debris to the flanks. Over many events, the trapped material builds up along both sides and creates walls with a central groove. In this view, some double ridges are fault scarps that have been armoured by their own talus and strengthened by ice cement. Small gullies that cut down the outer flanks and end in tiny aprons are consistent with this slow accumulation picture. Ridges influence the near-surface environment once they exist. When sunlight warms the uppermost grains by a small amount at local noon, tiny hops of vapour move frost from warmer spots toward cooler shadowed ones. The trough and the outer flanks collect this frost and brighten relative to the plane. Charged particles that sweep along the magnetic field of the giant planet interact with the surface in ways that depend on local electric conditions, which can vary across ridge relief. Slight differences in how grains charge and discharge can change how fast surfaces darken under irradiation. Over long spans, these effects allow troughs to keep a distinct tone even when mechanical relief has softened. Endings of ridges link them to the larger behavior of the shell. Some ridges taper smoothly into the planes with walls that sink and a trough that fades. Others fork with one wall continuing along a new azimuth, while the other dies out as if the direction of maximum tension rotated during growth. Some ridges merge into chaos patches. There the paired walls break into tilted roughs that lie within a smoother matrix, which implies that the corridor became warm and weak enough to disrupt as a unit. In other places, a pair blows out into a wider stripe with internal slices and grooves marking the first steps of band formation. These transitions show that ridges, bands, and chaos are related outcomes of the same broad controls of stress heat and brine supply. Double ridges also serve as markers for the flow of heat from below. Where the supply of tidal heat to the base of the shell is higher than average, the pump that moves brine runs more often, and ridges grow taller and more continuous. Where the supply is lower, ridges are lower and more broken, as if the pump pauses often. If slow overturn in the lower shell brings warmth upward in broad cells, ridge chains can align with the limbs of those cells. If cooling from above strengthens the lid, ridges become narrow, and the trough holds less frost because openings are smaller and less frequent. In this way, a map of double ridges becomes a quiet proxy for pathways of heat and for regions of relative softness within the shell. Over long spans, ridge fields age with the rest of the surface. Micrometeoroid strikes pock the crests and plant clusters of tiny pits. Sublimation under low sun rounds sharp edges and lowers small peaks. Frost cycles move bright grains from crests into troughs. The net result is a slow drift from crisp relief to muted relief. Because new ridges keep forming where stress and heat allow, the surface shows both young, sharply paired lines and older, softened pairs. Cross-cutting and superposition record the order of events with clarity. A younger pair crosses an older pair without much disturbance, and the faint offset in the planes between them preserves the small steps taken during each growth episode. Taken together, the picture remains specific and calm. Double ridges form where tidal stress opens and closes fractures within a layered shell that holds briny pockets and zones of warm, weak ice, upward movement of slush-freezing expansion, inclusion of wall fragments and gentle drainage together build two walls and a central trough. Variations in salt content, grain size, heat, supply, and local fault motion explain the many local forms. Links to bands and chaos show that ridges belong to a family of processes that distribute strain and move material through the shell without breaking the surface wide open. The result is paired relief that repeats across the globe, marks the slow breathing of the ice, and keeps a clear record of how stress and brine work together over many quiet cycles. Chaos terrain appears as fields of jumbled plates that sit within a smoother background and interrupt the usual order of plains, bands, and double ridges. From above, each field has an irregular shape, sometimes nearly round, sometimes stretched into a loose corridor, sometimes branching like a pool that has flowed into small bays. The edges are seldom sharp lines. They are more often soft embayments that cut into the surrounding plains and swallow earlier lineations. Inside the field, blocks preserve the older surface patterns they carried before being moved, so faint bands, small ridges or grooves can still be traced across single plates, even though the plates no longer fit together like pieces of a single sheet. The contrast between orderly lines on the individual blocks and the disorder of their collective arrangement gives chaos terrain its name and its distinctive, easily recognized look. The size of plates ranges widely. Some are only a few hundred meters across and look like chips that have broken from a larger slab. Others reach many kilometers across and hold complete segments of earlier belts, with their internal textures still visible. Plate outlines are rarely perfect shapes. Many are roughly polygonal with rounded corners as if fracture guided the first breaks and later softening blurred the lines. Along plate margins, low scarps, short ramps, or narrow moats can appear each only a small fraction of the total plate size, but important for reading the small changes in level. Where moats are present, they trace thin, dark rings that help pick out plate shapes even when lighting is not ideal. The background that fills the space between plates is smoother and finer in texture than the plates. It often shows faint flow like markings, very low hummocks, and small streaks that run parallel for short distances before fading. In bright light, the background looks slightly darker than the plates, which can indicate either a change in grain size or a thin coat of impurities that settled with the material that filled the gaps. In low sun, the background reveals shallow swales and soft rises that lack the angularity of the plates. Together, these subtle relief patterns suggest the background behaved as a soft fill that later became firm while the plates kept the relief of the older surface that they carry on their backs. Color variations add another quiet signal. Most plates match the pale tones of nearby planes with only slight dulling from age. The background and plate edges, in contrast, often carry thin brown to rust stains that gather in low spots and along lee sides where tiny grains can settle from weak winds of vapor. The stains are not dramatic, but they are persistent. They are strongest where the terrain has been opened and filled multiple times. These color zones help to define the outer contacts of a chaos field and to distinguish it from wide bands which are darker over their whole width and tend to contain internal slices arranged in a more parallel fashion. Contacts between chaos fields and surrounding features vary with place and tell the local order of events. A double ridge can run into a chaos field and then break into offset stubs attached to separate plates, which shows that ridge growth was interrupted when the field formed. A band can be cut, and its inner textures appear on several plates now arranged at new angles, which shows that the band is older than the chaos. In other places, a chaos field is cross-cut by later straight fractures that ignore the embayments and plate edges as they pass through, which shows a younger episode of stress. These relations are clear and repeat across many examples, so the fields serve as readable time markers that fit into the larger sequence written across the shell. The surface within chaos fields is not rough in a sharp way. Relief is gentle. Plate interiors carry small pits and low domes, similar to those on nearby planes, but these forms are often muted as if they experienced a brief warm phase before cooling again. Some plates are tilted a little so their shadows lengthen on one side at low sun, while the opposite edges sit nearly flush with the background. Narrow radial cracks can run part way across a plate and stop, suggesting stress that did not reach failure across the entire block. Small fans of bright frost sometimes drape the down sun sides of scarplets and collect in moats whose shadowed floors remain brighter than their rims for longer each day. Chaos fields show variety in distribution. Near some longitudes, many small patches pepper the plains like a chain of lakes spread along a preferred direction. Elsewhere, one large province dominates a region with a few outliers scattered beyond its margins. High latitudes host fields with more arcs in their plate edges, while equatorial belts host fields with straighter cuts and more rectangular outlines. These patterns align loosely with the larger network of stress directions inferred from ridges and bands, as if the same background forces that opened cracks and fed slush along them also guided where plates were free to drift a small distance before coming to rest. The density of impact craters within chaos fields is low, and where a crater does exist, it is often distorted. Round rims kink where they meet plate boundaries, Floors are not level but rise or fall as the block beneath them tilts relative to neighbours. The background can lap partway up a crater wall like a shallow embayment, which shows that the fill arrived after the impact and did not retain the exact outline of the earlier surface. These gentle distortions help to confirm that plates moved and background rose while the field was active, and they help to place the field in time relative to scattered impacts in the region. Edges of chaos fields can carry halos of secondary disturbance. Beyond the main embayment, the surrounding planes may sag slightly. Double ridges bend or taper as they approach, then resume beyond the far edge, as if they crossed a zone of weakness or warmth that softened their usual expression. Tiny parallel grooves, each only a few tens to hundreds of meters long, may appear outside the field and align with the field's longest axis, then die out with distance. These flanking signatures are not universal, but when present they strengthen the sense that chaos is not a simple hole in a rigid sheet, but a zone where the near surface behaved differently for a time and then returned to normal. Within some fields, clusters of small, nearly circular openings dot the background between plates. These openings are shallow, lac-raised rims and can be partly filled with bright frost. They tend to occur near places where plate edges converge or touch, as if the background pulled apart slightly after most movement had ended. In other fields, short ridges, a little like miniature versions of the larger double ridges, run along plate margins for short distances and then vanish into the background. These minor features give texture to the field and provide added clues about the last small motions before the surface stiffened again. Dot light plays a strong role in how chaos is seen. Under high sun, the subtle relief within the background fades, and the field becomes a map of plates picked out by colour and texture differences. Under low sun, the fine relief emerges and moats, ramps and tiny scarps cast lines of shadow that sketch plate edges with clarity. Repeated views at different solar angles strengthen the reading of plate shapes and of background flow, and help to separate real relief from colour contrasts. Over long times, the cycles of illumination, frost migration and grain growth work together to soften edges and reduce brightness differences, so the youngest fields are often the most vivid, and the oldest are subdued though still distinct. In summary of appearance, only chaos terrain is a quiet register of disturbance that did not shatter the shell but rearranged its upper layers. It is built of plates that keep the memory of earlier surfaces set within a smoother fill that carries soft textures and slight stains. It meets the surrounding planes with embayed margins, interrupts earlier features, and is itself crossed by later lines. Its relief is low, its shadows are fine, and its differences in tone are gentle yet persistent. It varies in scale and outline but keeps the same essential elements wherever it is found. Without naming a cause or assigning a detailed mechanism, one can say with care that chaos fields look like sites where the near surface became mobile for a time, allowed pieces to shift, allowed new material to settle and firm, and then handed the surface back to the usual slow processes that maintain planes, bands and ridges across the rest of the bright shell. Whether jets of water vapour reach space above the shell remains an open question, and the answer is approached through signs that are subtle rather than scenes that are plainly seen. A plume in this setting means a column or cloud of vapour and tiny ice grains that rises from a vent and then settles back or drifts away. The surface gravity is gentle enough that vapour can arc high above the ground without leaving the moon forever. Yet the vacuum is strong enough that any liquid exposed directly will flash to gas and freeze at once. The search therefore looks for brief faint traces against a dark sky, and for quiet fingerprints left in light and charged particles rather than for crisp silhouettes. One line of evidence comes from measurements of light at wavelengths that water splits or scatters in distinctive ways. When a star or the sun lies behind the limelight that grazes the edge may dim more than expected if a thin veil of vapour hangs above a vent. In other cases, energetic particles strike rare gas near the surface and make it glow faintly in ultraviolet colors that betray oxygen or hydrogen produced when water is split by radiation. There are times when the dimming or the glow appears where a vent would be plausible, often near lines of long fractures in the southern hemisphere. Yet the signals come and go. A pass that hints at vapor on one day is followed by a pass with no such sign on another day, even at nearly the same place. This irregularity can be read two ways. One reading is that vents may be intermittent and weak. Another reading is that the line of sight and the background conditions of light and charge particles can change enough to confuse the test. Because both readings are reasonable, caution remains. A second line of evidence comes from measurements of the magnetic and electric environment close to the body. If a cloud of water vapor rises and meets fast-charged particles that stream along the giant planet's field lines, the cloud becomes ionized. Ionized gas bends the paths of charged particles and induces small changes in the local magnetic field. Instruments that sense these changes sometimes record small sharp departures from the pattern expected for a smooth airless body. The departures look like what a short-lived cloud could cause. However, the plasma environment itself is complex and varies with the position of the Moon within the larger magnetic system. It is possible for background fluctuations to mimic part of the signature. Sorting one from the other takes many passes and careful modelling. Results to date contain cases that fit a local cloud very well, and other cases that do not require one, which again leaves the door open but not settled. A third set of clues is more direct yet still tentative. Images taken when the limb is backlit can be searched for threads or puffs that project above the edge. There are a few instances where faint protrusions have been reported along fracture belts. The forms are not dramatic. They sit at the edge of detection, and it is hard to rule out small alignment effects with surface topography, or scattered light from the instrument. Repeats at the same site are rare. In the absence of repetition, a conservative reading holds that such images are suggestive but not decisive. Thermal patterns offer a fourth approach. If a vent releases vapor from a shallow source, the active flow can carry heat toward the surface, and the immediate vicinity of a vent could appear slightly warmer than its surroundings at night. Maps of surface temperature show small warm spots near some long fractures, yet roughness and grain size can also make a place look warm after sunset, because rough ground traps light in shadowed pockets during the day and releases it slowly at night, and because large grains hold and release heat differently than fine grains. Without a way to separate texture from true heat flow in each case, the presence of a warm pixel alone cannot prove a vent. Dust and tiny ice grains provide a fifth hint. A detector that counts strikes by small particles sometimes registers a few more hits than expected when passing near the body. Those excess grains could be tiny fragments lofted from the surface by a recent burst and then spread along the orbit. They could also be part of the broader ring of debris that circles the planet, or even grains shed from the spacecraft itself. Sorting these sources is difficult because counts are low and paths vary. As with the other methods, some passes point toward a local source while others do not. If vents do reach space from time to time, a straightforward mechanism exists to power them. Tidal stress opens a fracture by a small amount. Briny water or slush held at shallow depth rises into the opening. When exposed to the near vacuum, that liquid flashes to vapor and throws tiny crystals upward. The flow cools rapidly and chokes itself by freezing along the walls, which narrows the throat and ends the episode. The cycle can then repeat on the next stress maximum, or it can pause for many cycles until pressure or geometry again favor release. The shell need not be thin from top to ocean for this to happen. A near-surface lens of brine fed slowly from below can vent modestly without a direct wide-open connection to the deep. This picture matches the small scale and intermittent nature of the hints. It also matches the absence of tall, persistent geysers, like those seen on a smaller moon nearer to the planet with famously active jets. A vent, if present here, is likely to be short, weak, and rare. The landscape near suspected sites supports this quiet view. Many possible sites lie along large double ridges, where a central trough could serve as a line of weakness and a cold trap for returning frost. Others lie at the edges of chaos fields where plates pulled apart and may have left fractures that reach a little deeper than average. Stains within these zones suggest that material from below has visited the surface in the past. Bright frost patches that look fresh against duller surroundings appear along some grooves and at the feet of small scarps. None of these marks requires an active plume today. All of them are consistent with low-level exchange within the shell that sometimes reaches close to the sky. A careful standard for proof helps to frame the present state of knowledge. One would like repeated detections at the same place with the same method under different viewing angles. One would like different methods to agree at the same site within a short span of time, such as a change in light at the limb, plus a small magnetic departure, plus a faint patch of fresh frost on the ground below the putative column. One would like to see a signal that follows tidal phase appearing when fractures are most open and fading when they are most closed, with a repeat that holds over many orbits. Pieces of this standard have been met at times, but not all at once, in a way that silences alternatives. Until that happens, the conservative and honest reading is that water can reach space at least sometimes, but the strength, frequency, and locations remain uncertain. The implications of even modest vents are practical and local rather than grand. Vapor that rises will mostly fall again within a short time, seeding the nearby ground with fine frost that brightens troughs and lee slopes. Tiny grains of ice and salt may settle out beyond the immediate vent line, faintly staining the plains along preferred directions as winds of charged particles sweep by. If vapor carries dissolved gases, a fraction may linger for a while as a very thin envelope near the ground and then break apart under radiation into oxygen and hydrogen that escape, with the heavier oxygen staying longer as a sparse near-surface population. These effects shift textures and tones at small scales and help to explain the patchy nature of brightness and colour around long fractures. In total, the present case for plumes stands on several narrow pillars that bear some weight but leave gaps. Light can dim at the limb in ways that fit vapour, yet not every attempt sees it. Fields and particles can shift in ways that fit ionized water, yet background changes can mimic the same pattern. Images near the limb sometimes show slight protrusions, yet they lack routine recurrence. Warm spots at night exist, yet they can arise for more than one reason. Grain counts rise on some passes, yet the source is not always clear. In this situation, a calm answer respects both the positive signs and the limits of each method. The shell likely breathes weakly into space through rare vents along long-standing lines of weakness, but that breathing is neither loud nor regular. It is another quiet part of a quiet world, traceable when geometry, timing, and instruments align, and invisible when they do not, leaving only a thin record of frost stain and subtle change along a bright, cold skin. Radiation at the surface makes reactive molecules that can be carried downward through the shell, and this quiet traffic provides a way to link light and charged particles at the top to chemistry in dark water below. The making of oxidants begins where energetic electrons and ions from the giant planets sweep past and strike the uppermost grains. Sunlight also helps by splitting bonds with photons in the ultraviolet part of the spectrum. When these agents meet water ice, they break some molecules apart and allow fragments to rejoin in new forms. Among the products are molecular oxygen, ozone, and hydrogen peroxide. These oxidants lodge within the outer skin of the surface, adhering to grain boundaries and coating pore walls. They are stable enough in the cold to linger until they are moved or consumed. That movement is slow but steady, because the surface is never quite still. Tiny impacts stir the topmost layer. Daily cycles of faint warming and cooling drive vapor to hop from sunlit grains to shadowed ones. Tides flex the crust and open and close hairline fractures by small amounts. Over long spans, these small actions add up to a gentle conveyor that can bury grains, connect pores, and draw near-surface material downward by short steps. The depth of initial production is shallow because radiation and ultraviolet light lose strength with distance into the ice. The richest band of products lies close to the top. To reach deeper levels, oxidants must hitch rides on carriers that can pass beyond that skin. One carrier is brine that forms in microcavities where salts have lowered the local melting point. When a fracture opens, slightly pressure drops and a little liquid appears along the walls. That liquid dissolves surface-made oxidants that it encounters as it seeps inward. When the fracture narrows and the liquid freezes again, some oxidants are trapped within the new ice. Repeats of the cycle build thin veins and lenses laden with these reactive species at depths greater than the reach of direct radiation. Another carrier is porous ice itself. Grain boundaries and connected pores can wick small amounts of vapor and liquid downward under slight pressure differences, especially where the temperature gradient points from warm interior to cold exterior and then reverses with time. The process is slow, but the spans of time available are long. Over many cycles, shallow oxidants can migrate grain by grain to deeper parts of the shell. Downward motion can be more decisive where whole plates of surface material founder. In belts where new bands spread, older crust can be drawn downward along narrow zones, a behavior that resembles subduction in broad outline. Observations show places where a swathe of older terrain appears to vanish beneath a younger band. If such foundering occurs, it offers a direct path for oxidant-rich surface layers to descend to great depth. The extent and frequency of this behavior remain debated. Some researchers see strong signs in a few corridors, while others note that most of the shell does not show clear recycling. The cautious view holds that foundering may be local rather than global. Even if it is rare, it would still carry a concentrated package of surface chemistry into the warm part of the shell, where fluids are mobile. Convection within the lower shell offers a broader, gentler route. Warm, weak ice rises in wide cells, while colder, stronger ice sinks around the edges. Surface material that has been slightly darkened and charged by radiation can be folded into the sinking limbs over spans of time and carried downward by many kilometers. As it descends, that ice warms and softens, and its oxidant cargo begins to dissolve into intergranular brines. When the rising limbs of convection deliver warm ice toward the lid elsewhere, some of the dissolved load is returned upward and refrozen into the near surface. In this way, convection can act as a slow exchange that both feeds the interior with oxidants and reworks the oxidant budget near the top. The result depends on the balance between the rate at which products are made at the surface, the rate at which they are consumed at depth, and the vigor of overturn within the shell. Once in the warm part of the shell, or the ocean, oxidants meet reduced materials and react. The rocky floor likely hosts minerals such as iron, bearing silicates and sulfides that give up electrons. Warm water in contact with that rock can carry dissolved ferrous iron hydrogen and reduce sulfur compounds. When oxidants descend from above, they accept electrons from these species and release energy in the process. The details of each pathway depend on the mix of salts in the water, the temperature, the pH, and the availability of catalytic surfaces. Hydrogen peroxide is a strong agent that can oxidize many reduced species quickly once it reaches liquid water. Molecular oxygen is less reactive in cold, dark water without catalysts, yet it can still support slow reactions or be stored as a long-lived pool that participates when mixed with fresher fluids from the rock. Ozone is short-lived once dissolved, and thus acts mainly near the point where ice meets liquid. The rate at which oxidants arrive at depth is likely small per unit area, but significant when summed across the globe and across long spans. Production at the surface is continuous because radiation never stops. Transport downward is intermittent but persistent through fractures, porous networks, and slow overturn. Consumption at depth is also continuous where reduced species are present. This sets up a quiet competition that can be framed as a budget. The surface is a source. The shell is a conveyor. The ocean and the rock are sinks. If the shell is very thick and overturn is weak, arrival at depth is slow, and most oxidants are recycled within the upper shell before they can reach the water. If the shell is thinner in corridors and fractures are well connected, oxidants arrive at depth more often, and the ocean becomes more oxidizing near its roof. Salts influence every step. If the ice contains sulfate or chloride salts, its melting point is lower, and brine pockets form more readily to carry dissolved oxidants. Salts also change density. Brines that become enriched in oxidants and some dissolved ions can become heavier than surrounding fluids and thus tend to sink along connected pathways, delivering their load downward. On the other hand, if oxidants react quickly near the top of the ocean, with reduced material carried upward from the rock, they may be consumed in a thin layer and never penetrate deeply. The structure of the ocean matters here. If the ocean is stratified with a cold, slightly salty lid over warmer layers, the oxidants may remain trapped near the top until mixing events occur. If the ocean mixes more readily, the oxidants can spread and reach the rock-water interface more often. Surface-made oxidants do not travel alone. Along with them come radiation products made from other constituents on the surface. Sulfur-bearing molecules likely arrive from the giant planet's volcanic moon and are implanted in the outer grains. These can be converted by radiation into a range of oxidized sulfur forms that stain fractures brown and rust. When these species enter the shell, they join the broader chemical traffic and alter the acidity and redox state of the brines. Organic molecules, if present at the surface from impact delivery, suffer damage under radiation and break into smaller fragments. Some fragments are reactive and can join the chemistry of brines. Others are destroyed or locked into mineral coatings. The net effect is to seed the upper shell with a varied set of reactive species that together shape the chemistry of any fluid that passes through. Where the shell opens and closes along double ridges, the evidence of exchange is plain. Bright frost lines the troughs and thin stains flank the walls. These marks imply that material from below has reached the sky, and that material from the sky has returned below at least a shallow depth. Each small episode of flow carries oxidants from the surface further into the shell and brings up salts and other solutes that later reappear as colours along fractures. Chaos fields likewise record exchange. When plates drift and settle within a soft matrix, the voids between them fill with material that likely held a mixture of dissolved ions and trapped oxidants at the time of freezing. The uniform texture of the background within chaos fields suggests that this refrozen fill smoothed earlier contrasts a sign that fluids had time to equilibrate chemically before locking into place. The overall picture is patient and specific. Radiation makes oxidants in the skin of the ice. Small motions of grains, pores, and fractures allow those oxidants to step down into the shell. Larger motions of plates, bands, and convective cells allow packets of oxidant-rich material to travel farther. In warm ice and liquid water, oxidants meet reduced species from the rock and from hydrothermal fluids, and react, releasing energy and producing new dissolved products that join the circulating brines. The balance between source conveyor and sink decides how far from the surface these oxidants can reach, and how long they persist once they arrive. No single path is required. Many narrow paths act together, guided by heat, stress, and salt. Each leaves a trace on the surface and within the shell. Read together, these traces show that the bright crust does not isolate the ocean completely. It filters salts and feeds, passing a slow rain of reactive molecules from the realm of light and charged particles into the quiet interior where water, rock, and time wait to use them. The surface carries gentle variations in color across the bright shell, and these variations point toward hydrated salts and sulfur products that have moved with brines and then weathered in the open. Most plains look blue-white and crisp where grains are fine. Along long fractures and at the flanks of double ridges, thin bands of brown, tan, and grey appear sometimes as a narrow fringe and sometimes as a broader halo. Within chaos fields, the smoother background often shows a faint rust cast, while the embedded plates keep paler tones that match nearby plains. In wide bands that cut older ground interiors look darker and slightly redder than their margins, and small grooves inside the bands hold alternating streaks that keep their deeper tone at all angles of light. These stains are the residue of dissolved materials that have risen with brines frozen in place and then been altered by radiation. Where lineations are dense and have opened many times, these stains are strongest, as if many cycles have carried new solutes to the surface and left them to age. Maps that compare brightness across many colors show that these zones differ from clean water ice. Clean ice reflects strongly at blue colors and keeps a smooth curve into the near-infrared, while stained ground shows broad, shallow departures that point to water bound within salts. Mixtures that include sulfates, chlorides, and carbonates can each shift those features in small ways. On this shell, the signals are faint but consistent where stains are clear to the eye, so the cautious reading holds that hydrated salts are present at least in thin coatings or in grains within a matrix of ice. In some corridors, the tones lean yellow-brown. Simple salts such as sodium chloride, when trapped in ice and exposed to strong radiation, can darken toward hues that resemble these belts. Elsewhere, signatures match hydrated sulfate salts, a natural outcome when water interacts with rock and later freezes. A thin layer of sulfuric acid hydrate may also be present where sulfur-bearing particles have struck the surface for long spans. These products can mingle within a single patch at scales too small to resolve. Spatial patterns add further clues. Stains concentrate on the hemisphere that faces the oncoming flow of charged particles, while the opposite hemisphere looks cleaner and bluer. Near the poles, the overall tone brightens as small grains are favored by cold yet subtle belts of darker ground still trace old stress paths. In ridge corridors, troughs tend to be the darkest lines, as if briny mists have condensed there again and again. Where single pairs cross an otherwise plain surface, halos are narrow and fresh and bright. Frost often softens the contrast. Chaos fields show pale plates set in darker matrix, which suggest that the fill carried more dissolved material at the time it froze than the rafts of older crust. The matrix also looks smoother and less granular than the plates, as if salts impeded the growth of large ice crystals during freezing and left a fine-grained darker solid. Color gradients around bands and chaos fields fade with distance, which implies that the source of solutes is local, and that diffusion into the plains is limited by cold and by a lack of liquid pathways far from the feature. Daily warming and cooling move vapor by tiny hops from warmer grains to cooler grains. This slow wind of molecules gathers coatings in lee pockets and shaded slopes so halos widen on the down sun sides of low relief. Floors of shallow moats around chaos plates look slightly darker than the rims, as if the smooth fill held more solute at the time of freezing, and then gathered more coating afterward. Some long stains run with belts of cycloidal ridges at high latitude, perhaps marking corridors where the lower shell has stayed warm for long spans and kept brines near at hand. Other stains march with old band interiors, whose darker fabrics resist brightening by fresh frost. In this way, colour becomes a faint shadow of the thermal and mechanical history written into the ice. They show that places with strong brown halos also carry the broad signs of bound water within salts, while cleaner planes show the smoother signature of pure ice. In a few tracts, narrow lines display hints of chlorine-bearing compounds, a match to what briny water might leave as it freezes. Elsewhere, relations favour sulfate-rich mixtures that would be expected if water has circulated through rock for long spans. Across all maps, one lesson repeats: where the shell has opened, moved and sealed many times, the salt signal is strong. Where the shell has stayed closed and cold, the signal is weak. That lesson fits a slow cycle from ocean to shell and back. Deep water in contact with rock picks up ions. Tidal stress and warm pathways move part of that water upward as brine or slush. Near the surface, the mixture freezes and leaves salts behind in tiny veins and on grain surfaces. Radiation then alters those salts and darkens them, and the faint wind of vapour moves some of the altered grains by short hops into lee pockets. Later, when fractures open again, part of the near-surface material drains downward or is pushed aside into bands carrying its chemical memory with it. None of this requires a torrent. It proceeds by many small steps that add up to quiet but persistent change in tone. The present view keeps to what the surface shows. It shows colour that clusters along fractures within band interiors and around chaos fills. It shows spectral signatures that match hydrated salts and sulfur products in those places. It shows contrasts between leading and trailing sides, between high and low latitudes, and between crowded belts of ridges and open plains. It shows that fresh frost can mask stains for a time, and that age and radiation restore them. From these descriptive facts, a grounded picture is drawn. Brines circulate within the shell and sometimes touch the top. Salts ride with them and take their place in the skin when the water freezes. Radiation and tiny vapour winds then adjust the colour and brightness, leaving narrow lines and soft halos that trace the paths of exchange. By reading those lines and halos with patient care, the shell reveals that it is not a sterile lid but a filter that lets chemistry rise in thin layers and settle again, marking its work with hues a little warmer than the ice around them. Beneath the ice lies a hidden ocean that rests on a rocky floor, and the contact between liquid water and rock is an active surface where minerals and fluids meet. The rock is not uniform. It is likely a mixture of silicate minerals similar to those in the mantles of terrestrial planets, along with iron-rich phases and sulfide grains. Over time, natural radioactivity in these rocks and heat from tidal flexing warm the interface and allow water to penetrate small cracks and pores. When water at high pressure and moderate temperature meets silicates, it alters them by leaching cations such as magnesium, calcium and sodium, and by taking up silica. When water meets iron-rich minerals, iron dissolves as ferrous ions. When water meets sulfides, sulfur species enter solution. The result is a fluid enriched in reduced chemical species that can react with oxidants delivered from above. The circulation of water along the rocky floor can be driven by thermal differences. Where heat escapes, water becomes buoyant and rises. Where regions are cooler, water sinks to replace the lost volume. This cycle, even if slow, continually brings fresh fluid into contact with fresh mineral surfaces. If the rock contains olivine, a common silicate, a reaction called serpentinization can occur. In this process, water reacts with the mineral to form serpentine and magnetite, and releases hydrogen gas. Hydrogen is a reduced species with potential to drive many reactions if it encounters oxidants. Serpentinization also generates small amounts of heat, which helps to sustain circulation. Over long spans, these reactions can transform the mineral makeup of the uppermost mantle and produce a steady flux of dissolved hydrogen into the ocean. The rocky floor may also host fractures that reach deeper, allowing localized upwellings of warmer water. Such sites can act like hydrothermal vents, though on this moon the temperatures may be lower than at Earth's seafloor vents. Even at moderate temperatures, reactions between rock and water can liberate hydrogen, methane, and reduced metal ions. As these fluids rise into the broader ocean, they mix with colder brines and spread their chemical load. The ocean water itself is not pure but saline. Dissolved ions likely include sodium chloride sulfate carbonate, and others derive from rock alteration. The balance of ions sets the density, freezing point, and electrical conductivity of the water. The conductivity measured indirectly through induced magnetic fields matches a solution that is salty to a degree similar to Earth's seawater or greater. Salinity stabilizes the liquid phase by lowering its freezing point so the ocean can persist beneath the ice, despite the great cold above. Within the ocean, chemical gradients arise wherever fluids of different composition meet. Reduced species such as hydrogen and ferrous iron emerge from the rock. Oxidants such as oxygen or peroxide may descend through the shell. Where these meet, energy is released. The amount of energy depends on how much of each species arrives and on how they mix. The interface between rock and water is thus a dynamic place where minerals alter gases, form, and solutes exchange. Over time, crustal rock can become coated with alteration products such as clays, carbonates, and oxides. These coatings trap some elements while releasing others. The thickness of these alteration layers depends on how fast new rock is exposed by fractures and how vigorous circulation is. If circulation is slow, thick alteration rinds can seal pores and reduce further reaction. If circulation is steady, fresh surfaces continue to be exposed and the flux of dissolved species remains high. The vertical structure of the ocean likely reflects both heat and chemistry. At the bottom, near warm rock, water is enriched in reduced solutes and may be slightly hotter. Rising plumes of this water spread outward and mix with overlying layers. If the ocean is deep, stratification can result with denser, saltier and warmer water below and fresher, colder water above. This stratification can trap chemical gradients and keep them in place for long spans. If mixing is stronger, gradients may blur, but reactions still proceed wherever new fluids meet. In either case, the ocean is not homogeneous, but a structured body with layers of different properties. Minerals at the floor play another role. Iron sulfide grains can act as catalysts that speed certain reactions between dissolved species. Surfaces of oxides can absorb molecules and release them later under different conditions. These catalytic effects are modest but matter over long timescales and large surfaces. They allow reactions to occur at rates greater than would be expected in open solution alone. They also create feedbacks where the alteration of one mineral fosters the release of ions that then help alter another mineral. This web of slow interactions builds a complex chemical environment at the base of the ocean. Heat supply from below may vary in both space and time. Tidal flexing within the rock can concentrate in belts where stress is highest. These belts can host warmer regions that drive stronger circulation. If the total flux of heat rises for a time, more hydrothermal flow may occur, and the supply of reduced species to the ocean increases. If flux falls, circulation wanes and gradients flatten. Such variations may leave subtle records in the chemical layering of the ocean and in the textures of alteration products on the floor. Another important detail is pressure. The ocean lies beneath many kilometers of ice, so the pressure at its base is high. High pressure changes how minerals dissolve and how gases behave. Hydrogen that is released at the floor can remain dissolved at concentrations higher than in shallow water. Carbon dioxide and methane behave differently as well. These properties ensure that the fluids rising from the floor carry significant loads of dissolved gases that can later be released when mixing lowers the pressure. Gas bubbles may form at interfaces within the ocean or along the base of the shell, and when they do, they can drive small local flows that stir the water further. Observations from afar cannot see these processes directly. They are inferred from the need to balance heat magnetism and chemistry, and from the parallels with what is known about rock-water interactions on Earth. Yet the logic is firm. Water in contact with rock at high pressure and modest temperature will react. The products of that reaction will include dissolved hydrogen, reduced metals, and altered minerals. These products will move into the ocean, join with salts already present, and meet oxidants carried downward. The outcome will be a steady creation of chemical gradients that shift in time and space as tides heat and fractures change their patterns. The rocky floor is not inert. It is a partner that shapes the chemistry of the ocean above it, by giving and taking, by dissolving and precipitating, and by trading electrons in reactions that proceed without pause. In this way, the base of the ocean beneath the ice is both a boundary and a source, a quiet yet persistent factory of dissolved matter that keeps the liquid water from being uniform and keeps it linked to the deep interior of the moon. Heat made inside the moon must find its way through the shell to reach space, and the paths it takes determine both the structure of the ice and the forms that appear at the surface. The simplest path is conduction, the direct flow of warmth through a solid. In the uppermost kilometers where the ice is cold and stiff, conduction is the main mode. A steep temperature gradient holds across this lid with the surface near absolute zero, and the base of the lid warmed slightly by the deeper shell. Conduction is slow, so the lid remains brittle, and stores stress rather than yielding to it. Below this lid, where temperatures rise toward the melting point of salty ice, conduction alone is not enough to move the full supply of tidal heat. Here convection can begin. Convection is the overturning of material in broad, slow cells. Warm ice that becomes buoyant creeps upward, while colder, denser ice sinks to take its place. Even though the flow is measured in centimeters per year or less over spans of millions of years, it carries significant heat. The balance between conduction in the lid and convection in the deeper shell explains why the crust behaves as both a rigid plate and a mobile mass. In zones where tidal heating is high, convection can be vigorous. Upwelling limbs of convective cells press against the base of the lid and deliver both warmth and any dissolved solutes carried in brines. The extra heat weakens the base of the lid and makes it easier for fractures to open. Where convective upwelling aligns with tidal stress, double ridges and bands become common. Downwelling limbs, in contrast, draw colder ice downward and can pull surface material with them, recycling altered grains and trapped gases into depth. These motions erase old patterns slowly, but provide the deep mixing that prevents the shell from growing too thick. Chaos terrains may mark spots where upwelling and local brine intrusion together soften the lid enough for plates to drift. The geometry of convection depends on shell thickness. In a thinner shell, cells are smaller and heat moves more directly upward. In a thicker shell, cells are broader and heat spends more time in the interior before reaching the top. Models that match observed surface features often call for shells of several tens of kilometers, in which convection is active below a brittle lid only a few kilometers thick. The resulting structure allows stress to be transmitted across great distances while still providing local softness where heat and brines rise. Diapirs are another expression of heat movement. A diapir is a blob of warmer, lower density ice that rises through colder, denser ice. As it rises, it pushes aside the surroundings and creates small domes or pits at the surface. On this shell, swarms of low domes and shallow pits that dot the plains are consistent with diapirs a few kilometers across rising from the convecting zone. Each diapir carries warmth and impurities, and when it cools it leaves behind a smoother patch with slightly different texture. Over time, diapirs can cluster and form fields that mark the long-term activity of the deep shell. Brine pockets within the shell provide still another path. Where heat is concentrated, salts within ice lower the local melting point and allow small reservoirs of liquid to form. These pockets can move upward slowly as surrounding ice creeps downward. When they near the surface, they may intrude into fractures and contribute to ridge building or chaos. When they freeze, they release latent heat, which feeds back into the local temperature field and can sustain further mobility. Evidence for brine pockets comes from the disrupted textures of chaos and the stains along ridges. Such features point to repeated episodes where pockets froze and left behind both mechanical disturbance and chemical residue. The transport of heat by these pockets is modest in absolute terms, but focused in narrow corridors that leave strong marks at the surface. The overall heat flux from the interior to space is constrained by thermal measurements from orbit. Bright surfaces radiate most of their energy in the infrared, and careful mapping shows that emission is consistent with a global average heat flow, similar to that expected from tidal dissipation in the shell and rocky interior. Local departures from the mean suggest that some regions lose more heat than others. Bands and chaos fields tend to align with higher flux, while broad plains with fewer features show lower flux. This patchiness matches the idea that heat travels unevenly, guided by convection diapirs and brine pockets, rather than by a uniform gradient alone. The interaction between heat transport and surface stress is a key factor in shaping terrain. Where heat is high, the lid thins and weakens, allowing tidal stress to open fractures repeatedly. Where heat is low, the lid thickens and strengthens, resisting fracture, but storing stress until larger breaks occur. This interplay explains why the surface hosts belts of dense ridges separated by quieter plains. It also explains why chaos appears in some provinces but not in others. The shell records not only the total amount of heat, but also how that heat is distributed in space and in time. Radiation damage at the surface interacts with heat from below. If a warm plume brings up fresh brines, the frost that settles after venting can cover darker radiation products and renew the surface brightness. If heat is weak, radiation has time to darken the grains before the next renewal. The competition between darkening from above and brightening from below contributes to the patchwork of tones seen across the globe. Heat transfer also influences the stability of the hidden ocean. If the shell conducted alone, cooling might freeze the ocean within geologic time. With convection, diapirs and brine motion, heat moves more efficiently, and the shell remains thinner, which in turn allows the ocean to persist. The balance is delicate yet steady. Tidal input provides a constant source, and varied transport mechanisms distribute it upward without closing the ocean. This dynamic equilibrium has likely held for many millions of years. In short, the ways that heat moves through the shell are layered and complex. Conduction through the brittle lid sets the cold surface. Convection in the deeper ice carries most of the load. Diapirs rise as focused blobs that dot the plains with domes and pits. Brine pockets migrate and freeze, leaving ridges, chaos and stains. Together, these processes explain why the shell shows both rigidity and softness, both order and disruption. They ensure that the hidden ocean remains liquid, that the surface keeps renewing itself in pieces, and that the link between deep interior and cold exterior remains active. The shell is not static ice, but a mediator of heat, a slow, moving filter that accepts energy from within and sends it upward in forms that light instruments and patient eyes can read, probing the unseen requires tools that sense gravity magnetism, radio echoes and thermal patterns, each of which reveals a different aspect of the shell and the ocean beneath. Gravity is read through the path of a spacecraft as it flies by. Small accelerations and decelerations betray variations in mass within the Moon. If the shell were extremely thick and stiff, the shape of the body would reflect frozen tides from long ago, and the gravity field would remain locked to that shape. If a liquid ocean lies beneath the shell, then the outer ice can move slightly in response to tides raised by the giant planet, and the gravity field shifts with each orbit. Tracking the tiny motions of a spacecraft with radio signals allows the detection of these changes. From such data, scientists derive the presence of a decoupling layer that fits a global ocean. Magnetism provides another window. As Jupiter's magnetic field sweeps past, it induces secondary fields in conductive layers inside the Moon. Instruments detect the strength and orientation of these fields. Matching the observations requires a salty liquid ocean close to the surface. The induced signal cannot be explained by rock or by pure ice, which are poor conductors. By mapping the changes across many passes, the depth and salinity of the ocean can be constrained within ranges that are consistent with laboratory data for brines under pressure. Radar sounding offers a direct way to probe the shell. High-frequency radio waves sent from an orbiter can penetrate ice for many kilometers, bouncing back from boundaries where composition or temperature change. On Earth, such radar reveals the base of glaciers and lakes beneath polar caps. On this Moon, the challenge is greater because salts in the ice absorb radar energy and reduce the depth of penetration. Still planned instruments are expected to see tens of kilometers deep enough to map internal layers, find zones of convection, and perhaps even glimpse the top of the ocean if conditions are favorable. Radar will also reveal the thickness of the brittle lid by showing where strong echoes arise from the transition to warmer ice below. Thermal mapping from orbit uses infrared sensors to measure how surface temperatures change through day and night. Differences of only a few degrees can indicate variations in grain size, texture, or subsurface heat flow. Persistent warm anomalies that do not fade with time of day may point to active processes below, such as recent brine intrusion or ongoing convection that delivers heat close to the lid. Coupled with visible imaging, thermal data help to distinguish between roughness effects and true internal heat sources. Each method has limits, and that is why their combination is powerful. Gravity senses the whole body but at low resolution. Magnetism is sensitive to conductive layers, but cannot alone define their exact thickness. Radar can trace internal layers, but may be blocked by salts. Thermal mapping reveals surface expressions but not their full depth. By bringing these methods together, scientists can test one inference against another. If gravity implies a decoupled shell, magnetism should show a conductive ocean. If radar finds a warm lower shell, thermal mapping should show surface signs above it. Agreement across methods strengthens confidence, while mismatches highlight places where assumptions need refinement. Flybys have already provided first hints of the ocean through magnetism and gravity. Future missions plan to orbit for months or years, gathering dense tracts of data. Each pass at a new angle will map part of the hidden interior, and together the mosaic will approach a global view. Repeated measurements over time will capture changes tied to tides, allowing the thickness and mobility of the shell to be tracked. Instruments will aim radar at chaos fields to see whether their interiors are warm and brine-rich, at double ridges to test whether liquid lenses exist below, and at smooth planes to measure convection cells. Magnetometers will pass over both leading and trailing hemispheres to capture the full range of induced responses to Jupiter's field. Gravity instruments will focus on how mass is redistributed when tides rise and fall. Thermal sensors will watch the night side for persistent hotspots. Together, these approaches turn indirect sensing into a coherent picture. The role of uncertainty is accepted openly. Salinity can vary widely and still produce similar conductivity. Grain size in ice alters radar penetration in ways that are not fully predictable. Roughness can mimic warmth in thermal maps. Gravity fields can be perturbed by local topography as well as by deep structure. To cope, data from multiple instruments are compared against physical models that account for these factors. Only solutions that satisfy all constraints at once are retained. This iterative process gradually narrows the ranges of shell thickness, ocean depth, and heat flow. Even then, ranges rather than single numbers remain the norm, reflecting the true state of knowledge. The measurements also inform models of stability. By tracking the thickness of the shell in many regions, it becomes possible to see where the ice is likely thin and active, and where it is thick and quiet. By measuring the induced magnetic field, it becomes possible to infer salinity, and hence the likely strength of convection in the ocean. By mapping internal reflectors with radar, one can tell whether convection is broad and steady, or focused into diapirs. By mapping heat flow, one can tell where brines may be gathering close to the surface. These are not guesses, but direct consequences of what each instrument records. The unseen ocean is thus made visible through a chain of inference that begins with data and ends with models grounded in physics. In this way, unseen depths are described in calm, specific terms. Beneath the bright lid lies an ocean whose conductivity, thickness, and salinity are measured indirectly but securely. The shell above is mapped as a layered structure with a brittle top and a convecting base. Heat paths are traced through domes, ridges, chaos, and bands. Each method confirms part of the story, and together they reveal a world that is not static, but in steady exchange between inside and out. These methods also set the stage for future work. Landers may one day test the surface chemistry directly drilling or melting into shallow fractures to taste brines trapped in ice. For now, the focus is on orbital sensing, which respects the difficulty of touching a body so cold, so hard, and so far away. What emerges is a view that is both detailed and cautious. The ocean is there, salty and global. The shell is layered brittle above and mobile below. Heat moves through conduction, convection, diapirs, and brine pockets. Brines rise, oxidants sink, chemistry meets at depth. Each conclusion comes not from a single bold measurement, but from the quiet accumulation of many small consistent signals. The unseen is revealed step by step, and the record of those steps is as clear as the data and models that support them. When considering whether the hidden ocean can host habitable conditions, a careful checklist is applied. The first item on the list is the presence of liquid water, and this condition is satisfied by multiple lines of evidence. Gravity magnetism, surface geology, and thermal balance all point toward a global briny ocean beneath the ice. The second item is the presence of chemical energy. On this moon, energy sources include oxidants made at the surface and carried downward, reduced species made at the rocky floor, and carried upward and tidal heat that maintains circulation. The third item is the presence of essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon can arrive in comets and be stored in surface ices, or be dissolved from rock. Nitrogen may be less abundant, but small amounts could be delivered by impacts or be trapped in salts. Phosphorus can be released from minerals at the floor. Sulfur is implanted from outside and circulated within. With all these elements present, at least in trace form, the raw materials exist. The fourth item is stability. For habitable conditions to persist, the ocean must remain liquid for spans long enough for chemistry to build complexity. Tidal heating ensures that the shell does not freeze entirely, and radioactive decay in the rock provides a steady background of warmth. Geological features such as young ridges and chaos fields show that the shell has been active in recent time, meaning that heat flow and exchange continue today. These four items together support the cautious statement that habitable conditions are possible, yet many details remain open. The actual concentrations of oxidants and reductants are not known. The rate at which they meet is not measured. The depth and mixing state of the ocean are not resolved. The amount of each essential element that is soluble and available is uncertain. To frame these uncertainties, models explore a range of cases. In one case, oxidants trickle down efficiently, reductants rise strongly, and mixing is vigorous. In this optimistic case, chemical energy is plentiful and spread widely. In another case, oxidants are trapped near the lid, reductants are consumed near the floor, and mixing is weak. In this conservative case, chemical energy is limited to thin layers, and the bulk of the ocean is inert. Reality may lie between these ends, with some regions more active and others more quiet. The shell itself plays a role in habitability. If plates founder into the ocean, they deliver oxidants and organics in concentrated packets. If convection is broad and steady, it circulates materials but dilutes concentrations. If diapirs rise, they bring brine lenses close to the surface where they can freeze and trap chemistry, storing it until the next episode of warming. If fractures open, they allow small bursts of exchange that feed local reservoirs of solutes. These processes provide both continuity and variety, which may be important for sustaining reactions. The rocky floor is a second key. Serpentinization produces hydrogen steadily wherever olivine and water meet. Sulfides can release reduced sulfur species. Basalts can yield ferrous iron. Hydrothermal circulation, even at moderate temperature, stirs these species into the ocean. Each of them can react with oxygen peroxide or other oxidants to release energy. The persistence of these reactions over spans of millions of years would maintain chemical disequilibria, which is one hallmark of habitable conditions. The presence of salts changes the picture in subtle ways. Chlorides and sulfates alter the freezing point and the density structure of the ocean. They influence how convection works by stabilizing or destabilizing layers. They provide ions that participate in chemical reactions and can act as buffers that moderate pH. They also determine how conductive the ocean is, and thus how strongly it responds to the giant planet's magnetic field. The details of salinity therefore matter for both physical and chemical reasons. Impacts add another variable. Comets and asteroids deliver carbon compounds, nitrogen-bearing ices, and phosphorus-rich minerals. On impact, some material may be destroyed by heat, but some may be buried in the shell and preserved. Over time, slow descent of altered crust can feed these materials into deeper levels. In this way, external delivery supplements internal supply. Radiation at the surface, though destructive to complex molecules, also creates oxidants that are crucial for energy budgets. Thus, the same process that breaks organics can indirectly support habitable conditions by generating reactive species. Assessing habitability does not mean declaring life is present. It means checking whether conditions that allow complex chemistry exist. On this moon, the checklist items of liquid water energy elements and stability each have support, though each with uncertainty. The balance of evidence is enough to keep the question open and active. Future missions aim to refine these checks. Instruments that sniff for water vapor above fractures may detect dissolved gases carried upward. Instruments that map surface chemistry at finer scales may find stronger signatures of salts and organics. Instruments that probe gravity magnetism and radar may define ocean thickness and mixing state. Together, such data will narrow the ranges of possible conditions. It is also possible to frame habitability in spatial terms. The ocean is not likely uniform. Near the floor, reduced species dominate. Near the lid, oxidants dominate. Where mixing is strong, gradients blur and energy is spread widely but at lower concentration. Where mixing is weak, gradients sharpen and energy is concentrated in thin layers. Both situations offer opportunities for reactions, though of different kinds. In a stratified ocean, the interface between oxidant-rich upper water and reductant-rich lower water may be a narrow but potent zone. In a mixed ocean, reactions occur throughout at a lower rate. Either case provides settings where chemical disequilibrium can persist. In summary, the careful checklist for habitability is not met in every detail, but is not contradicted any essential way. Liquid water is supported by multiple lines of evidence. Energy sources exist from both above and below. Elements are present through rock radiation and impacts. Stability is granted by tidal heating and radioactive decay. What remains is to measure amounts and rates. Until that is done, the correct stance is patient openness. The ocean beneath the ice may be a quiet reservoir of chemistry that has lasted for millions of years, balanced between sources and sinks, stirred by tides and heat and filtered by the shell. Its conditions are neither certain nor entirely unknown. They are constrained by data framed by models and described by careful inference, all of which leave room for the possibility that the dark water beneath the bright shell is habitable in principle. Interior models attempt to explain the structure of the shell and the ocean, but they differ in how thick the shell is, how heat moves within it, and how quickly exchange occurs between surface and depth. In the thin shell model, the brittle lid is only a few kilometers thick, and beneath it lies a convecting layer that may be only several more kilometers before reaching liquid. In this picture, stresses at the surface easily penetrate downward, fractures may reach near the ocean, and brines can rise to shallow depth with little resistance. Such a shell can explain the apparent youth of the surface, the scarcity of large craters, and the presence of chaos terrain that looks like disrupted plates floating in slush. The drawback is stability. For a shell this thin would conduct heat too efficiently and might freeze the ocean without constant tidal heating. Advocates of the thin model counter that tidal heating is indeed strong and sustained by orbital resonance, and that convection helps regulate thickness so it does not vanish or grow too large. In the thick shell model, the ice is tens of kilometers thick and behaves more like Earth's lithosphere above a convecting mantle. In this view, surface features form not because cracks reach near the ocean, but because warm ice diapairs rise partway and deform the surface. Double ridges are explained as products of shallow brine lenses rather than direct plumbing to the ocean. Chaos terrain is explained as localized melting within the shell rather than wholesale collapse to liquid. The thick shell model offers stability because conduction across many kilometers is slow, and the ocean can persist for billions of years even if tidal heating fluctuates. The drawback is that chemical exchange between surface and ocean may be limited, making habitability less dynamic. A third class of models accepts that thickness may not be uniform. In these variable shell models, the ice is thinner in active belts where heat and stress are concentrated, and thicker in colder provinces where less heat is delivered. Such models explain why chaos bands and ridges cluster in regions while other regions remain smoother. They also explain why magnetic data and gravity data allow a range of thicknesses rather than a single number. In variable models, the shell behaves like a patchwork quilt with corridors of mobility embedded within wide blocks of rigidity. Exchange between surface and ocean is then focused in the active corridors, while most of the shell remains a barrier. Each class of model has implications for how features form. In thin shells, ridges can form by direct intrusion of ocean water that freezes in fractures. In thick shells, ridges form by brine squeezed from internal lenses and by shear along faults. In variable shells, both processes occur but in different places. In thin shells, chaos is true plate rafting on near liquid. In thick shells, chaos is melting within the shell. In variable shells, chaos arises where thickness locally decreases. Evidence from surface morphology and spectral stains supports aspects of each, so debate remains. Heat transport also differs between models. In thin shells, convection cells are narrow and rise quickly, so domes and pits appear often. In thick shells, convection cells are broad and sluggish, so surface expressions are muted. In variable shells, domes and pits appear in belts with large smooth planes in between. Gravity and magnetic data can distinguish between end members, but often allow both. For instance, a strong induced magnetic signal requires a shallow ocean, which can occur with a thin or variable shell, but is harder with a very thick one. Gravity tides that match observations also imply decoupling, which again allows both thin and variable cases. Impact crater relaxation supports a warm base, but not whether it is a few kilometers below or many tens. Because of this, uncertainty remains and is openly stated. The speed of exchange is another dividing line. Thin shells allow rapid communication with oxidants sinking, and brines rising in spans shorter than 1,000,000 years. Thick shells restrict communication with materials taking tens or hundreds of millions of years to cycle. Variable shells allow local fast exchange and global slow exchange. These rates matter for habitability because they set how often chemical gradients are renewed. If renewal is rapid, disequilibrium is constant and reactions continue. If renewal is slow, gradients may flatten and reactions pause until a new pulse arrives. Interior models also differ in their implications for mechanical behavior. Thin shells would yield more easily to tides and show larger amplitude surface motion. Thick shells would suppress motion, but might preserve stresses that release in bursts. Variable shells would allow local mobility but global stiffness. Observations of surface lineations, especially cycloidal ridges, suggest that stresses do penetrate deeply enough to produce complex patterns, which favors shells that are not excessively thick. Yet the existence of long-lived smooth planes suggests that parts of the shell must resist for long spans, which favors thicker parts. Thus both ends find support, reinforcing the idea that variability is likely. Models can be tested by future missions. Radar sounding can directly measure the depth to warm ice in chaos fields and double ridges. If radar shows echoes from near liquid at shallow depth, thin shell models gain weight. If radar shows only warm but solid ice, thick models are favored. Magnetometers can measure the induced response more finely, and if the response points to very shallow, brine-thin or variable shells are again supported. Gravity tracking can detect how tides flex the body, and if the flex is large, thin shells are consistent. If small, thick shells are consistent. Thermal images can map heat flow, and if heat is patchy, variable models are supported. If smooth, thick models are supported. Until such data arrive, the conversation remains balanced. Thin shells explain surface youth and possible plumes. Thick shells explain stability and muted exchange. Variable shells explain patchiness and diversity. Each captures part of the truth, and together they frame the range of possibilities. The prudent stance is to accept that the shell may be both thinner and thicker, depending on where and when, and that processes seen at the surface are the product of this layered and varied reality. Models will continue to evolve as more data arrive, but already they provide a framework that connects geology, chemistry, and physics into a single calm narrative. Beneath the bright crust lies an ocean whose presence is certain, but whose details are still contested. The shell above it is not a single uniform thickness, but a structure that allows debate, evidence, and inference. By weighing thin, thick, and variable shells against each other, researchers describe the boundaries of the possible and prepare for the next steps in seeing what is truly hidden. The shell and the ocean beneath it move and change on scales that instruments can only hint at, and reflection on what remains unknown helps to frame the calm picture that data provide. One open question is how often the shell recycles itself. Some features suggest that plates of older ice sink beneath newer bands carrying altered surface material into the interior. If this is common, then chemical exchange between surface and ocean is efficient, but if it is rare, then most oxidants remain trapped near the top. Observations show both possible signs of recycling and vast plains where no such evidence is seen. The balance between these views is not settled, so the true global rate of recycling remains a quiet uncertainty. Another open question is whether plumes are active today. Hints of vapor clouds above the surface exist, but they are faint, irregular, and not always repeatable. If plumes are real and persistent, they offer a way to sample the ocean directly from orbit. If they are rare or absent, then exchange between the ocean and the sky is far weaker than some models assume. Current evidence does not resolve the question, so the possibility of plumes remains open but unproven. The thickness of the shell is another area of debate. Estimates from gravity magnetism and surface forms overlap in a broad range from several kilometers to many tens of kilometers. Thin shells are easier to explain in terms of geology, but thick shells are easier to explain in terms of stability. The variable shell model with thinner corridors and thicker provinces may reconcile the two, but the exact distribution of thickness is not yet measured. Until radar and gravity data are gathered at higher resolution, the thickness of the shell will remain one of the central uncertainties. The state of the ocean itself also holds questions. Its salinity is inferred from conductivity, but the exact mix of ions is not known. Chloride-dominated water would behave differently from sulfate-dominated water in terms of density, freezing point, and chemistry. The degree of stratification is unknown. A layered ocean with stable boundaries would host sharp gradients that could concentrate energy but limit mixing. A well-mixed ocean would distribute energy more evenly, but at lower concentrations. Both states are plausible, and neither is confirmed. The interaction of rock and water at the floor is another quiet puzzle. Serpentinization is likely but not directly observed. Hydrothermal vents may exist, but at temperatures far below those on Earth. How much hydrogen, methane, and reduced iron reach the ocean depends on fracture networks, mineral makeup, and heat flow, all of which are poorly constrained. Yet these details matter for the budget of chemical energy. Without them, estimates remain wide. Surface chemistry is also uncertain. Spectral data show hydrated salts and sulfur products, but the identity and abundance of these species are still debated. Some fits point to magnesium sulfates, others to sodium chloride, still others to mixtures that include sulfuric acid hydrates. The leading hemisphere shows different patterns from the trailing hemisphere, partly due to radiation environment and partly due to local geology. Without samples in hand, the interpretation of these spectral signatures remains tentative. Another question is how long the ocean has persisted. Tidal heating is steady because orbital resonance maintains eccentricity, but over billions of years orbital interactions can shift. Radioactive decay in rock declines with time. Models show that oceans can last for hundreds of millions to billions of years, but whether this particular ocean has been stable for the entire age of the solar system, or only for part of it, is not known. If the ocean is ancient, chemical evolution has had immense time to proceed. If it is younger, perhaps born after a later orbital change, then its history is shorter. Both scenarios remain consistent with present evidence. The role of external delivery is another uncertainty. Impacts bring organics, carbon, nitrogen, and phosphorus, but the fraction preserved is unclear. Some may be destroyed by heat, some buried and preserved, some recycled into the shell. Without knowing the frequency and scale of delivery, the contribution of impacts to the chemical budget is left open. The rate of surface renewal is debated as well. Few craters suggest youth, but not all regions are equally active. Some plains may be tens of millions of years old, others much younger. The average resurfacing rate controls how quickly new material is exposed and old material is buried. Without precise counts and ages, the resurfacing history remains only broadly described. Even the details of heat distribution are uncertain. Average heat flux is constrained, but local patterns may vary with time. Convective cells may drift. Diapirs may rise and fade. Brine pockets may appear and freeze. The shell is dynamic, but how dynamic at any given time is not resolved. Some episodes may be more active, others quieter, leaving a record that is incomplete. These uncertainties do not diminish the confidence in what is known. The presence of a global salty ocean is secure. The existence of a shell that convects below a brittle lid is secure. The presence of hydrated salts and sulfur products on the surface is secure. The action of tides as the main heat source is secure. The rest remains open not because data are absent, but because the processes are subtle, the signals faint, and the interpretations many. Science moves within these boundaries with patience, building models, testing them, discarding some and refining others. Each uncertainty is not a flaw, but a measure of where further work is needed. Missions planned will carry radar to probe depth magnetometers, to track induction gravimeters to measure tides, and spectrometers to map chemistry. These will reduce ranges, confirm or refute models, and shift open questions into answered ones. For now, the uncertainties provide context. They remind that the picture of this moon is partial, drawn from distant passes and limited data. They remind that even with modern tools, the hidden ocean remains hidden, its details known only by inference. And they remind that in such a situation, calm reflection is required. What is known is presented with care. What is not known is stated plainly. Between the two lies the true state of understanding a world beneath the ice, revealed enough to know it holds water and energy, but still veiled enough to invite continued study. It is a state of knowledge that is incomplete, yet sufficient, quiet, yet compelling, precise, where possible and open, where not leaving the narrative poised between certainty and mystery, without rushing to close the gap.